Jerome Friedman is Emeritus Institute Professor at MIT. As an experimental physicist, his PhD was supervised by Enrico Fermi, followed by participation in a pioneering experiment showing parity violations. And, in the course of the famous MIT SLAC collaborations, carried out a series of measurements of inelastic electron scattering, and particularly deep inelastic electron scattering from the proton and the neutron. This provided the first direct evidence of the quark substructure, the partons, the quarks, and ultimately the gluons. And I have to add a personal note about during this time when all of the MIT SLAC experiments were being carried out. I was lucky to have Professor Friedman on my PhD committee, and right during this time. And at my defense, he seemed really sleep deprived. He seemed really tired, but yet very happy. So, of course, it was because he stayed up all night reading my thesis, right? and so happy reading it. Well, of course, it was the time, this exciting time, where he was looking at, doing the experiments, looking at the data of, all of that famous, the deep inelastic parton, constituent demonstrations, the evidence for constituents that came out of it all. For his work, and not my thesis, Professor Friedman shared the 1990 Nobel Prize in Physics. He went on to do much work on testing the Standard Model and put himself, of course, in a perfect position to give us a lecture on quarks. Please join me in welcoming Professor Friedman.
As you can see, the title of the talk is Exploring the Structure of the Proton. And the reason I have this title is because we weren't looking for quarks. In fact, in those days, nobody believed in quarks for various reasons. And we just wanted to continue, just to understand whether the proton was a fundamental particle or not. So this story starts in 1966, when SLAC came online. We had been working with Caltech and SLAC for about 3 years, designing and building up the spectrometer system and the detectors. And we wanted to carry out a series of elastic measurements to measure the structure of the proton. And following the great pioneering work of Hofstadter in the 50s and 60s, in which he got the charge form factor and he got the RMS radius, so we went on to do this. So what were the models of the time? We had the nuclear democracy was the S matrix period, bootstrap, and there was a quark model that was independently proposed by Gell-Mann and Zweig to account for the success of the SU3 classification scheme. The quarks were the building blocks of the families of particles. And and the whole idea, as has been mentioned, is that no particle is more fundamental than any other particle. They're all equivalent in being basic. They were composites of one another. And from that point of view, you didn't have any little centers of charge in these particles, but you'd have sort of continuous charge distributions. And the quark model was there were 3 quarks at a time: the up quark, the down quark, and the strange quark. They all spin 1/2, and they had a strange business of fractional charges, and nobody really liked the idea of fractional charges in nature, but that's what it was. And of course, you had the baryons were 3 quarks, and the mesons were quark antiquark. But the question is, are quarks real? And what do physicists do when they have a new particle proposed? They look for it. They look everywhere. Accelerators, cosmic rays, the terrestrial environment, everywhere. And not a quark was found. And of course, everybody said, of course, this is kind of a ridiculous idea. Field theory doesn't work in the strong interactions. Quarks have fractional charges, and not a quark has been found anywhere. So why believe in quarks? And they looked at quarks as being more or less as a good mathematical representation of the SU3 families. But the old physics prevailed in terms of what the structure of these particles was. And here's a picture of SLAC. It was in operation at that time. It was 2 miles long. The experiments were done at end station A here. And as you can see, SLAC went over a superhighway here. It was quite a machine. It was 20 GeV electrons, very high intensity. The duty cycle was so bad that if you did experiments with the electrons, you could not do coincident experiments. So if you did an electron experiment, it would have to be inclusive. But nevertheless, we decided, here are the spectrometers that were built at the time. They were the largest instruments in physics at the time. In fact, here's the so-called 8 GeV spectrometer, and here's the 20, was 150 feet long. It was 2,000 tons. This was about 75 feet tall. The target was here, of course, and the things could move on rails. And we measured the form factor of the proton. And it turned out to be just a continuation of what had been measured at CEA and at DAISY. It really wasn't very interesting. Nothing new was discovered. And so at that point, we decided we will abandon elastic scattering and try something else. And we decided to do inelastic scattering, inclusive inelastic scattering, in which we only detect the electron. We wrote a proposal, and we brought it to the program committee, and they said, this is nonsense, this is ridiculous. You can't learn anything from elastic scattering. So the only way we could get the experiment to be done is to promise to measure the form factors of the resonances, the proton resonances, which we did and never published. In the meantime, we measured the inelastic spectra sort of as a background, and we snuck in some parts which were not background. And so we carried on these experiments. Now, it turns out that one can never really learn about the structure of the proton just by doing elastic, for the following reason. Elastic scattering gives a time average. And of course, if you have constituents moving around the proton, all you can see are distributions, charge and magnetic distributions. And that's what gives you the form factors. Friedman pointed out later, which was not really appreciated at the time, that the only way you could measure constituents is by having a large exchange of energy. You have to have a large exchange of energy to localize the constituents. And in fact, if you use the uncertainty principle, you can show that if you exchange 2 GeV, you can localize a constituent to 10 to the minus 14 centimeters, which is about 1/10 the size of the proton. And therefore, you start being able to see if there are specific charge centers in the proton. And therefore, you need deep inelastic scattering to really find constituents. Now, here are all the participants. There were about 26 over roughly five and a half years of work. There was roughly 10 people working on the experiment at a time. The blue names are from MIT, and the black names are from SLAC. The names with the underlying names were graduate students who worked on the project, and some of them went on to do really wonderful work in particle physics. All right, now I want to show the other co-leaders, Henry Kendall and Richard Taylor. Sadly, they are both deceased. Dick only recently, And I can say about them that they were wonderful colleagues and wonderful friends. And it was a great pleasure to work with them. Now, I'm going to use three invariants in terms of discussing what was measured. One was, these are relativistic invariants. One was nu, the energy loss of the electron, q square, the square of the form momentum transfer in the process, and m square, or w square rather, which is the invariant mass of the recalling system. So there were two major surprises. One was Bjorkane scaling, which has been mentioned. I'll speak a little bit more about it. And the weak q squared dependence of the cross sections. Now, Bjorkane scaling was a very, very interesting idea. It was quite mysterious in a certain sense because it came from a pretty obscure type of sum rule. I mean, it's been discussed. The real interpretation from a physical point of view was not clear, but it was something so interesting we had to test it, which we did. And when we started seeing evidence of it, of course, the program committee got quite interested, and we started getting as much time as we needed to do these experiments. And of course, there was the weak q score dependence of the cross sections, which was extremely interesting. And let me just, and here's a test. Here is not a test. This is a set of cross sections. As you go down from the top to the bottom, the average q square of these spectra get larger. And as you can see, the resonances are disappearing. And all you see after a while down here is a broad spectrum of scattered particles. And so this is sort of the behavior that was there. So let me say a few words about Bjorkane scaling. Just, if you look at the cross section, you have the Mott cross section, and you have the structure functions W2 and W1, and of course the Mott cross section comes from the photon propagator, but W1 and W2 basically depend upon the properties of the target, and so they're the main things of interest. In general, they should be properties. They should be dependent upon two variables. Let's say q squared and nu independently. The interesting thing about the Bjorkane scaling was that if you go to large q squared and large nu, these structure functions become just a function of the ratio. And that was an extremely interesting idea. And that was something that had to be tested. And that came out in 1967. And we tested it. And here's W1 and W2. You can see, the errors were large. These were difficult experiments to do. We had derivative corrections to put in, which actually at that time we were utilizing as much computing power as you would get on site. And of course, we found scaling. Now, since that time, it's, there is a deviation of scaling, which comes from QCD, which these deviations go as the log of q squared. The errors were too large, and the variation was, and the range of energy was not big enough to really see that. But so, from that point of view, we had scaling, and it was actually it came quite early. It started at lower kinematic values than was thought to be the case. And here's scaling. Here's, for example, omega equals 4, and you can see the q squared dependence is very, very flat, which was very surprising. Now, this is something I want to. This was of great heuristic value to look at this. Here is a electron scattering from carbon, and you see what you have here is you have the elastic peak, and then you have the excited states of carbon. And then you have this big continuum. And this big continuum is actually electron scattering from the individual nucleons. And so therefore, this scattering yield depends upon the form factors of these nucleons. Now let's look at elastic scattering, not elastic, but scattering from the proton. This is here we have the elastic peak here, and we have excited states, the resonances, and then we have this continuum. So one of the things that you would take away from this is there is the possibility that you might have constituents here too. And this is something that we wanted to look into. And so the first thing you do is to see what the q-squared dependence of this part of the curve is. Because after all, if there are constituents, that would give you an idea of what the form factor is and how big the system is, how big the constituent is. And here's the plot. And so here's the elastic form factor, which basically reflects the size of the proton. And here are the inelastic yields for various values of W. And you notice as W gets higher, this thing really flattens out. It curves over because there is a limitation in kinematics. It has to curve down at some point. But you notice how flat this is. And if you ask yourself, what gives a flat form factor? It's a point source. So this suggested the idea that maybe these cross sections are being held up as a function of q-squared by point constituents. So this became the idea where point constituents might be there. So now what happens is that old physics dies hard. And as soon as these results came out, both scaling and the weak q-squared dependence, there were a whole bunch of papers, vector dominance, resonance models, Reggie poles, diffraction models, which could be tweaked to try to get a flatter q-squared, and even perhaps even represent a bit of scaling. That was very hard. These things never really worked, but there was a big attempt to sort of, if you could probably keep tweaking them, maybe you could get the exact results. And that's what was going on at that time. However, we kept on measuring. And after 1970, we got more statistics. We also did scattering from deuterium. And we got a deuterium target, and then we did the analysis. We took into account the Fermi motions to try to get the structure functions correctly, in which we did. And we actually, I'm sorry. Wait. And here, for example, the scaling for the proton, the neutron, and the deuteron, they all scale about equivalently. So we're seeing the same thing. And we did the ratio of neutron over proton as a function of x. Now, x is the inverse of omega. So this is the modern scaling variant, because omega goes to infinity, so x goes from 0 to 1. And it's much more easy to use in this representation. And also it has another interpretation, which I'll talk about. But we notice that there is a linear drop, and at about 0.85, the value comes down to 0.3. Now, it turns out that when you looked at all these various models and try to find out what the ratio for neutron over proton would be, the only one which actually would survive was the quark model. And that would say that it could be as low as 0.25. And all the others seem to fail. And so most of these models actually were eliminated by this. I think almost all the models were eliminated by this. And so we have a quandary. All the models seem to fail, yet nobody believed the quark model. And it turns out that a contribution which helped resolve the puzzle, because it gave a physical picture to what was happening, was the part-time model of Feynman. And let me say a few words about it, because it was quite an interesting point of view. The idea was that you have a proton with partons in it, and so it's basically a field theory to begin with. The electron interacts with the parton. The partons interact among themselves and produce the garden variety particles that we all know, the Ks and the Ps, etc. Now, the thing which was interesting is that if the partons are point-like, they scale. You get scaling automatically. 2, that if you interpret the parton, that if the proton is moving in a reference frame, the struck parton, x is the fraction of the momentum carried by the proton of the struck parton. So there was an interpretation at that point to what the scaling function was. And therefore, let's say F2, which was it's the new sort of modern version of the structure function, is related to the momentum distribution of the partons in the proton. And so therefore, from the parton model, a physical model appeared. And so this started making sense from a physical point of view. So, but the point is, if partons are to be quarks, 2 things must be true. They must have spin 1/2, and they must have the fractional charges of quarks. So both things have to be taken care of. And so the first thing was to measure the spin, and for this we used the Callan-Gross sum rule, which related for spin 1/2 related F2 is equal to 2x times F1, and that could be measured. And we measured it, and it seems to be the case. So possible constituents in the proton would have spin 1/2. So that was already taken care of in the experimentally. Now, there was one other sum rule. I think this is a sum rule by Bjorkane and Pascos. And the idea was that actually if you do the F2 sum rule, it gives you the average charge of the up and down quark squared. But unfortunately, it also is proportional to the fractional momentum carried by the quarks. So that was a problem. But we decided we would evaluate it anyway because it would put a constraint on the situation. And the point is, if the quarks carried all the momentum, the answer should have been 0.28. But the answer came out to 0.14. So this suggested that if the fractional charges of the partons are those of the quarks, the partons or the quarks are carrying half the momentum of the proton. So this is still unsatisfactory, but another set of experiments help resolve this. The comparisons between the neutrino deep inelastic and the electron deep inelastic actually resolve this problem. Now, the neutrino work came from the large, heavy liquid bubble chamber Gargamel, which did work between 1971 and 1974 at CERN. And here's a picture of it. It was 5 meters long. It had 12,000 tons of freon, and it was quite a device. And here you can see here are the cross sections for both neutrinos and antineutrinos from those days, and the linear increase with energy implied it was scattering from point-like objects. So that aspect demonstrated that the neutrinos were being scattered by the same things that the electrons were being scattered from. And here is the result. Now the point is, you see, when you have a neutrino scattering from quarks, they don't scatter from the charges. They're scattering from the weak interaction constant, basically. So if you take the ratio, that ratio will depend upon the charges of the quarks. And so therefore, by doing that, you can evaluate it And the answer turned out to be 3.6. The first experimental evaluation was 3.4, plus or minus 0.7. This error decreased afterwards and by getting more data. But this result was announced at the London conference in, I think it was 1972. And this was, in a certain sense, the proof that the proton had quarks inside. Now, it turns that the neutrino work also shows some other things. First of all, the F2 sum rule for neutrinos gives the fraction of momentum carried by quarks. So it turned out to be, remember I said, for the electron charge distribution, charge measurement to be, to confirm the quark model, you'd have to have the quarks carry 0.5 of the momentum. Their answer is 0.49 plus or minus 0.7. There was another sum rule that neutrinos can do that electrons can, because there's a structure function related to the non-conservation of parity, F3. And if you do that sum rule, it should be equal to the number of valence quarks. And they got 3.2 plus or minus 0.6. So that's it. So partons are quarks. The partons are quarks. Spin 1/2. They have the right charges. And so, what was the model of the nucleon in those days? 3 valence quarks, a quark anti-quark C, the vacuum polarization, and gluons, which carry 50% of the momentum. At that time, both Weisskopf and Cudi did a model of the proton in which they included gluons for the first time, I believe, that any model did. And so those gluons would have to carry half the momentum. And so, however, new results require new theories. And there are 2 things that have to be taken care of. One, no free quarks have ever been found. So they're bound, most likely. And so therefore we have something called infrared slavery. 2, that when the electron and neutrino interact with the quarks inside the proton or neutron, these quarks are acting like they're free quarks. And therefore, we have to have something called asymptotic freedom, namely that as the energy gets higher, the interactions decrease. And so a new theory was required, quantum chromodynamics by Gross and Wilczek. David is here, and Politzer independently. And of course, quantum chromodynamics became, in a certain sense, half of the standard model. And so that is, in a certain sense, I would say, the culmination of the standard model, except for the discovery of the Higgs. So this is a brief historical summary of how this came about. Thank you very much. Okay. Okay.
Have a few questions. We have time. Yes, please.
So you mentioned that when you didn't find anything in elastic scattering, you looked for the inelastic sort of,
yes,
almost like, what else can we do? But you certainly must have had some idea or some expectation or some theoretical motivation, or was it just?
Okay, that's a very interesting question. I cannot speak for Henry and Dick, because I haven't spoken to them about it for years, and I don't remember exactly all the things that were said in those days. I suspect that Henry must have spent quite a bit of time talking to BJ, because I think they were roommates at that time. But I had a separate motivation. I had worked for a year measuring the Drell-Schwartz-Sum rule. And the Drell-Schwartz-Sum rule was that if you sum over all the excited states of the electron disintegration of the deuteron, you can find information about the ground state, namely the exchange force. So actually I had measured that, and I said to myself, well, if this works for the deuteron, why wouldn't it work for the proton? And so that's what gave me motivation. And then later I heard about sum rules that were being proposed by Bjorkane, and even Kurt Gottfried, who had a sum rule he had been developing. So that expectation was borne out by the fact that theorists were again working on sum rules for the proton, using all the excited states of the proton. But I'll tell you, when we started out the experiment, as I said, the program committee was very unfavorable, and I was told personally by people who I respected that if I continued in this direction, I would be ruining my career, because nothing would come of it. And so one has to be careful about what advice one takes from elders. So it worked out pretty well. And unfortunately, because it appeared to be so uninteresting, Caltech dropped out. Because they had worked with us on the elastic scattering, but they thought it was too uninteresting to get involved in. And as a matter of fact, the question came up as, what if you did inclusive scattering, what would you expect from the proton? What are you? Because when you do an experiment, you have to have a template to compare the results with to figure out what you're doing. So I went to a number of theorists to ask if they would be interested in calculating what kind of measurements would we get in terms of the continuum. And they wouldn't want to bother us. First of all, it's too complicated. It's not going to give you very much, and it's not worth the effort. And so I sat down and worked out a very, very simplified sort of set of expectations. And it was very simple. You take a electron, it emits a virtual photon. It's inclusive, so you have to put in the total photo production cross-section. You have to have a vertex function of q squared, but q squared has to have a distance to be essentially without a unit. And what distance do you have except the size of the proton? And if you do that, what you have is the total photo production cross-section times the photon form factor, because that's the only q squared you know anything about. And so we use that as the template. And then when we started doing measurements, it turns out that we got a factor of 2 bigger. Well, it's an approximation. Factor of 5 bigger. Well, maybe it wasn't such a good approximation. Then a factor of 10, 100, 1,000. Then it became quite clear we're looking at something else, and there's something else holding up the yields as a function of q squared, and that's when everybody got excited. And of course there was scaling, which was to us a mysterious thing, but it was extremely interesting. And I think BJ did a lot of talking around SLAC, helping convince the people who were in the power structure to let us do our work. So I think it was extremely helpful. So that's a long answer to your question. Yes.
Okay. So the story of your own experiment is fascinating, and I've heard before. What surprised me was the prominence of the Gargamel results as well in establishing that the partons really were quarks, and it was really interesting to hear. I just wondered whether that, clearly in the comparison between the SLAC data and the Gargamel data, was that something the experimentalists discussed, or was that entirely serendipitous?
I think from what I understand from Don Perkins, they heard about the SLAC results. I mean, the SLAC results the first results were published in 1968, and their experiment I think started in 1971, and I think it became quite clear that if you can do deep inelastic electron scattering, you can also do deep inelastic neutrino scattering. And I'm sure that motivated them, and of course they played a very important role in the whole business.
Given that Teggett Jones was on that experiment, who's from UCL, I'm surprised he hasn't told me that story so many times. So now I'm going to go back and tell him.
Well, he should have told him, because Don Perkins knows it very well.
Sure.
The program committee was having trouble to give you more time, and I'm just wondering what did they want to replace you with? What was the competition?
There was such a lineup of experiments to come in. There were plenty of people to take our place, and I don't remember all the experiments that were proposed in those days. But I guess they were kind to us because we had helped build the spectrometer system, and they probably were kind of charitable to us, saying that, okay, if you measure these resonances, you can have the time. But there were lots of users for the accelerator at that time.
So I want to echo a little about what you were saying about what the. Okay. Yeah, what you're saying about the climate at that time. I was working right down the hall from you, less distance than this room is, and we had no trouble getting experiment proof, which was to test. Okay, right here? Okay, all right. So we had no problem getting approved an experiment to do weak decay, a test of the weak decays, change in strangeness equals a change in charge, as a real test, a really hard, complicated experiment, which was going to be my great thesis, was my thesis. But, eventually by the time we published Gargamel, you and Gargamel had your results out. But in fact, almost no one was believing in the quark model at the time, and barely the parton model that was just basically explaining your data. And most of the people thought what was going on was quite quiet. I'm not surprised that.
Yeah, well, you see, the thing is that people did not think that field theory would work at all with strong interactions because of the coupling constant, and it's only because you have asymptotic freedom that that you can actually use QCD in a perturbative mode, and so from that point of view, the theorists were not very, very happy with the idea that. There were quarks inside, which implied a field theory. In a certain sense, in the S matrix period, I don't think people worried too much what was going on inside particles because they're all equally fundamental. It was just basically the relationship of one particle to another in terms of processes. And that's the way the whole world was looked at in those days. In fact, when I was a student at Chicago, I heard somebody say, I forget who it was, the strong interaction problem is so difficult, it'll take 50 to 100 years to resolve it. And that was probably about 1952. And the interesting thing was that by 1973, with QCD, the problem was solved. And sometimes progress comes much faster than people will anticipate. Some new breakthrough comes and things can yet be resolved quite quickly. There's another question back there.
I just want to add one thing to this discussion about the politics of the inelastic scattering. One name you have not yet mentioned is Wolfgang Kurt Hermann Panofsky, who was the director of the laboratory and an honorary member of your collaboration. And I think his support of the experiment, I think, was really
he was crucial,
element.
But he had to be careful because he'd worked with us, and so if you work with a group, you have to lean backwards, not to participate in the decision. And I think while I think he was very sympathetic, I really wonder how much he could have said within that committee. So it's an interesting question.
Pete had a reputation of brilliantly manipulating.
Oh yeah, he was
decisions of the program committee.
He was intelligent, super intelligent from all aspects of his activities. So I have no doubt that he was helpful, but it must have been a very delicate situation. He
was on the program committee for several years and saw Keith in action.
Yeah, but did you see him in action for himself? That's the difference.
Well, for this, what you're talking about, I don't think I was on the committee then.
Yeah. No, it was interesting.
Jerry, I just wanted to add a bit on the theoretical confusion at the time.
Sure.
People who thought about high energy scattering were mostly thinking about diffraction scattering, small angle, total cross section. That was the most important experiment in colliding protons and Reggie-Paul theory. Why? Well, that was one of the only few ideas that existed in theoretical studies of the strong interaction. And also, from an experimental point of view, that's where the data was. So most of the scattering data is at low momentum transfer. So experimentalists were delighted that theorists focused on that and regarded that as total, the secret of the strong interactions was to understand Reggie behavior and the total cross-section. Now nobody cares, or few people care very much. But if you look at, of course, diffraction scattering, or you get exponential fall off in the cross-section. You have s to the t or e to the t log s. So an exponential fall off in t, q squared. And so that was the prevailing, even without any real theory of what might happen when t is of order s. So it was sort of a conspiracy of theorists and experimentalists focusing on the wrong questions. Experimentalists were happy because most of the data was there. You could get really good statistics on low angle scattering. And theorists were happy because they had Reggie theory, some idea based on very general principles of analyticity and angular momentum and an energy which they could play with. And they totally went in the wrong direction.
That's very interesting, David. But I think that this sort of points to the idea that one has to be more speculative. There is this idea that there has to be a well worked out theory to test. And of course, a well worked out theory should be tested. However, there are times you can do some measurements and just be searching for something. And it's something that really wasn't anticipated. I think BJ had a term which I remember him using in a talk, something called planned discoveries and then discoveries. And a planned discovery is where there's a well worked out theory and you're out to confirm it. But there are also things that are discovered almost by accident, and there should be enough phase space left in the system to let people find these accidents. And I think that's a lesson for the future.
I want to add quickly to an addendum to what Dave said. It wasn't only the experimentalists and particular theorists. Richard Friedman, when he came to SLAC, he had invented the parton model for hadron-hadron collisions in order to interpret Reggie poles in his language. And then he learned about what was going on in SLAC, and overnight realized that electron scattering was a lot simpler than what he had been doing, and had, I'm sure, what I call
the mic a little closer to you.
Oh, okay. What I call an oh bleep moment, where bleep is a four-letter word that starts with S. And said, oh my God, I've been so stupid worrying about this complicated problem when electron scattering is so much simpler. So overnight, he worked out the parton interpretation of the local deep inelastic data.
Yeah, I want to make.
Let me just comment on the comment.
Okay. And then I'll cut in.
But nobody in doing hadron scattering was looking for jets or large PT processes. And they could have. I mean, there's no reason why they couldn't have, except that the statistics, that there was no theory, and that from an experimental point of view, why, if there's no theory, why look? I mean, I agree with your statement, but I think the sort of feeling perhaps was, especially on program committees, why do experiments where you're only going to get 2 or 3 events per year or per month when you can get thousands of events if you look at the forward direction? Yes.
But I do think it's unfair to say that the strong interaction problem that they were talking about is solved by QCD. Right. Certainly QCD underlies the neutron-proton interactions and all of the phenomenology that we know about hadronic interactions, but we can't calculate it from QCD. And so what happened was the new data changed the problem to the understanding the quark theory. And we've made huge progress there, and it's told us new things to look at and opened up huge new areas of physics. It's not that it answered all the old questions. It said those were not the questions we could answer with this approach, and gave us new ways to look and test and check the theory. And that's what we have done.
It's so now exciting for me to hear this discussion that I've got to stop before I get a heart attack. So, but please, thank you very much, Jerry, for a fantastic story that just was. In closing, I would like to say again, what an honor it has been to be associated with this first session. I'm looking forward, of course, to the next session tomorrow morning, but and I hope you've relished this afternoon as much as I have. But finally, please join me in thanking our entire cast of fantastic people. You know, Jonathan, Takaaki, Steve, Mary Kay, BJ, and Jerry. Thank you very much.